So, the first thing we're going to talk about is what's called hybridization. And hybridization is the combining of valence orbitals in order to achieve new orbitals of equal energy in order to form bonds. So, for instance, if we consider the CH4 molecule, carbon, its valence electron configuration, it's He 2s2 2p2. So the problem here is that when carbon is forming these chemical bonds here, it's using electrons from its 1s orbital and from two of its p orbitals. Because if we were to draw a little energy diagram, we've got your 1s, then we have the 2s, and then we have the 2p. The 1s is all full, the 2s is full, and then it's got some electrons in the 2p. But when carbon is actually forming 1, 2, 3, 4 chemical bonds, it's using its 1 2s orbital and all of its 2p orbitals. And the 2s orbital is lower in energy than a 2p orbital, then we would expect one of the bonds in CH4 to have a different amount of energy associated with it than the other three. But what happens is this process called hybridization, where instead of having a 2s orbital and three 2p orbitals, what it ends up making is 4 equally equivalent in energy, what are called sp3 orbitals, that it puts one electron into each of and then is able to make those bonds. It's called sp3 because it takes an s orbital and 3p orbitals in order to do this. So this is called sp3 hybridization. Actually, understanding how hybridization works is not really essential to answering the questions on the AP exam, however, because they don't really test your understanding of the actual concept. All you really need to be able to do is count what are called effective pairs. And effective pairs are either atoms or lone pairs attached to the central atom. So if you have two effective pairs, that's called sp hybridization, and the bond angle is 180 degrees, as in the CO2 molecule, where it's got two atoms attached. We don't count the double bond as part of that because in a minute we're going to talk about how double bonding works and why it's different from single bonds. sp2 hybridization is required for 3 effective pairs, such as in the BH3 molecule. It exhibits sp2 hybridization. And then sp3 hybridization is required for 4 effective pairs, and so the electron geometry is 109.5 degrees. CH4 is sp3 hybridized, as is the NH3 molecule, because it's got 1, 2, 3, 4 effective pairs on the NH3 molecule. So both NH3 and CH4 are sp3 hybridized. Then for dsp3 and d2sp3 hybridization, that's stuff that the AP exam doesn't expect you to know. That would apply to things that are based off of essentially the trigonal bipyramidal framework or the octahedral framework. So essentially, if you're built off of a linear framework, you're sp hybridized. If you're built off of a trigonal planar framework, you're sp2 hybridized. And if you're built off of the tetrahedral framework, then you're sp3 hybridized. So hopefully that gives you a good little overview of hybridization. The other thing we're going to look at is what's called formal charge. And formal charge is the difference between the valence electrons on a free atom. In other words, if you were just looking at nitrogen, for example, nitrogen has 5 valence electrons, carbon has 4, hydrogen has 1, oxygen has 6. So it's the difference between that and the electrons assigned to the atom in a compound. And so the formal charge is the difference between those. And the valence electrons that are assigned to an atom in a compound equals however many lone pairs it has plus half of the shared electron pairs. And I'll explain how we do that in just a minute. But the key thing to note is that a preferred Lewis structure is the one where each atom gets a formal charge as close to 0 as possible, and negative formal charges are on the most electronegative atoms, specifically things like fluorine, chlorine, or oxygen or sulfur would have the negative formal charges, and the less electronegative elements would have positive formal charges. But we want to minimize formal charge as much as possible. So let's consider a couple of examples. Let's consider first the NO2 minus polyatomic ion. Well, it could be arranged as NOO, or it could be arranged as ONO. And if we add up the electrons, nitrogen has 5 plus oxygen has 6 plus oxygen has 6 plus a extra electron for the negative charge, we're dealing with 18 valence electrons or 9 pairs. So we start drawing the Lewis structures 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have to do a resonance structure that looks like that, or this. Now, the other option is that if we had the nitrogen as the central atom, then the structure is going to end up looking like this. It's going to look very similar. It's just the difference is going to be the basis of formal charge. Now, the College Board is not going to expect you on the AP exam to come up with the different possible arrangements of Lewis structures. They're going to ask you to consider some possible Lewis structures and evaluate them on the basis of formal charge. So if they gave you these two options, they would ask you on the basis of formal charge, which one is preferable? So let's look at this. So if we look at the molecule over here on the left, if we evaluate for formal charge, nitrogen normally has 5 valence electrons. Well, in this molecule, it's got 1, 2, 3, 4, plus half of each of these. So that'd be 5 and 6. So if it has 6 electrons and it normally has 5, its formal charge is -1. An extra electron, and electrons are negative. For this oxygen, it's going to have 2 electrons here, plus half of that pair, that makes 3, plus half of each of those 2, that would make 5 electrons. Oxygen normally has 6 valence electrons, so it's short 1. It's a formal charge of +1. And then if we look at this other oxygen over here, it's got 2, 4, 6 electrons plus half of that pair, so 7. So it's got an extra electron, so that's -1 formal charge. And then if we evaluate the resonance structure associated with it, this nitrogen down here has 1, 2, 3, 4, 5, 6, 7 valence electrons, so that makes it -2. The oxygen in the middle is still going to have 1, 2, 3, 4, 5. It's going to be +1. And this one over here is going to be 1, 2, 3, 4, 5, 6. So that would be 0. So this is not looking good on a formal charge basis because nitrogen is not the most electronegative and it's got a negative formal charge, and oxygen's more electronegative and it's got positive formal charge. So let's see if this other structure on the right is any better. So if we look at this oxygen, it's got 1, 2, 3, 4, 5, 6 electrons. So that's a formal charge of 0. The nitrogen has 1, 2, 3, 4, 5. That's a formal charge of 0. And this oxygen has 2, 4, 6 plus half of 1. That's a formal charge of -1. Down here, it's going to be the exact opposite. The oxygen on the right is going to be 0, nitrogen is 0, and the oxygen on the left is going to be -1. So on the basis of formal charge, this structure is preferable because, first of all, it minimizes the formal charge. Most things have a formal charge of 0. And then you got a -1 and a -1. So hopefully that helps make a little bit of sense for formal charge. And so you just need to be able to assign formal charge and then look and see which one has the least formal charge. We're going to do a lot more work with this tomorrow, because tomorrow is going to be mostly dedicated to practice with this type of stuff. Next thing to look at is bond order. You don't need to know too much about this, but for bond order, a single bond has what's called a bond order of 1, a double bond is 2, a triple bond is 3. If you have a resonance structure, such as in the SO2 molecule or in the NO2 minus molecule, essentially each of these would have a bond order of 1.5, because it's not a double bond and a single. This would be a bond order of 1 and a bond order of 2. We'd call that a bond order of 1.5. And now for the last thing, the difference between what's called a sigma bond and what's called a pi bond. And keep in mind also, this is based off of the Greek letters sigma and pi. Sigma representing ultimately s orbitals and pi representing p orbitals. So in the localized electron model, which is what we deal with when we're drawing Lewis structures, sigma bonds are the strong bonds formed from overlapping of orbitals directly between the nuclei. So sigma bonds are essentially formed directly in line with the axis of the nuclei. So when we make these hybridized orbitals, or if we're dealing with a very simple molecule that only makes a single bond, like the dihydrogen molecule H2, it's an overlapping of s orbitals. These are very strong bonds. And then the pi bonds are weaker bonds, which are formed by the overlapping above and below the nucleus of the p orbitals. So to help explain this, let's take a look at, for instance, if you consider a single atom, it's got p orbitals, which are kind of shaped like this. And then there's one that comes out vertically. It's kind of hard to draw that one. They're aligned on the X, Y, and Z axes. Well, if you have two atoms that are bonding, keep in mind the orbital actually consists of one whole set that's aligned on the X, Y, or Z axis. When atoms are bonding, they first, in between them, will form a sigma bond. And then if they make a double bond, the double bond is formed by overlapping of p orbitals, where they would merge, for instance, this set of p orbitals or that set of p orbitals to make. If you overlap just one set of these, that's for a double bond. And if you overlap both this set and that set, that would be for a triple bond, because you have your original single bond and then you layer on some p orbitals on top of it. You cannot form another bond with this p orbital, because when these two atoms are bonded, these p orbitals, you've got the nucleus is in between there. It doesn't really allow overlap of those orbitals. Plus, the sigma bond is occupied in that space. So you only form uh, for pi bonds. It's only formed with two of the three sets of p orbitals. Now, the other key thing about pi bonds is that they prevent rotation around the bond. So sigma bonds are flexible. If you have a large molecule, it can bend and flex around the sigma bonds, but pi bonds prevent rotation of a molecule. It stops any twisting around. And that will become significant when we talk about isomerization. But if we go back, for instance, to the NO2 molecule, what we would say is that this molecule has two sigma and one pi bond. So this is a sigma bond, one of these is a sigma bond, and the other one is a pi. If we go back over here, the CO2 molecule has two sigma and two pi. BH3, it's just three sigma bonds. CH4, it's four sigma bonds. NH3, it's three sigma bonds. So a double bond is a sigma and a pi. A triple bond, for instance, in the carbon monoxide, has one sigma and two pi bonds.